Everyone, welcome to today's webinar, Quantum Computing. Are you ready for the future of computing? Hosted by the Internet Explorers of DSITNS4A of Technological University of the Philippines, Manila. First, I would like to introduce myself. I am Raer Gabriel Carisbertolata, but you can call me Sir Gab, and I am one of your hosts for today.
I'm his partner, James Vincent Grabador, also one of your hosts for today. Number 1, be respectful. Do not comment inappropriate things in the chat. Second, questions will only be entertained in the Q&A portion.
And that is all for our house rules. Simple lang naman. Simple to follow.
Yes,
Um,
guys.
that is it sa house rules natin. Let us all take a moment of silence and bask in the presence of the Lord.
Lead me, Lord, lead me by the hand and help me face the rising sun. Comfort me through all the pain that life may bring. There's no other hope that I can lean upon. Lead me, Lord, lead me all my life. Walk by me across the lonely roads that I may face. Take my arms and let your hand show me the way. Show the way to live inside your heart. All my days, all my life, you are my light. You're the lamp upon my feet. All the time, my Lord, I need you there. You are my light. I cannot live alone. Let me stay by your guiding love all through my life. Lead me, Lord. Lead me, Lord. Even though at times I'd rather go alone my way. Help me take the right direction. Take your road. Lead me, Lord, and never leave my side. All my days, all my life, you are my light. You're the lamp upon my feet. All the time, my Lord, I need you there. You are my light. I cannot live alone. Let me stay by your guiding love all through my life. You are my light. You're the lamp upon my feet. All the time, my Lord, I need you there. I just cannot live alone. Let me stay by your guiding love all through my life, all through my days. Don't leave me, oh no. Lead me.
Now, for the singing of the national anthem.
Mga kababayan, ang pambansang awit ng Pilipinas. Kayang magiging
May we call on Professor Maria Carmela Francisco, Head of Computer Studies Department, for the welcoming remarks.
Hello, everyone. I hope that everyone is well, especially after the Typhoon Paeng. Okay, so again, good afternoon. It is indeed my pleasure to join you here in your webinar and welcome the guests and participants. Hence, I'd like to enjoin everyone to listen and participate in this very interesting topic that our invited guest speaker will talk about. So this afternoon, our expert will make us better understand what quantum computing is, its powers, and how we can benefit from it. I hope that you will patiently stay until the open forum so vague aspects can be clarified. We commend at this point, I'd like to commend this IT group of students for organizing such seminar that adds value to your credentials that could maybe use as a leverage when you apply for job as you include it in your profile or CV. Sabi nga dito sa kanilang rationale or significance, no? However, given the immense potential of quantum computing, there may soon be a huge demand for skill in this field as both the workforce and technology advance quickly. No? So at least this will be the beginning, no? Getting the soft skill. Okay. So, please stay, grab this opportunity to learn free of charge. So, alam nyo naman ang mga seminar and the guest speakers, medyo, lalo especially this field, no? So, medyo kokonti pa yung experts. Kaya, I hope that you grab this opportunity. Sabi ko nga, to learn free of charge. So, again, enjoy your seminar, no? Good afternoon again and welcome everyone. Thank you.
Again, thank you to Ma'am Francisco for welcoming everyone participating in this event.
Grabe, partner. Mag-uumpisa na yung event na matagal na nating tinlano. Napaka nerve-wracking no? How about you, James? How do you feel, partner?
Same here, partner. Andito rin yung mga respected guests na mag-observe sa atin. So, need talaga natin galingan.
Yun, true. Now, without further ado, let us welcome our speakers for today. Our speaker for today, Mr. Corpus, is a quantum computing evangelist. Earlier this year, his group was recognized by One Quantum Global Community and was assimilated into the group as One Quantum Philippines, where he serves as the current president. Now, Mr. Bobby Corpus organized Quantum Computing Philippines in 2017 to promote awareness of Filipinos to quantum computing.
He is also a technical architect at Section 6, New Zealand, and was the innovation lead at the Enterprise Data Office at Globe Telecoms. He was a solution architect at Red Hat, a vice president and lead solution architect in Deutsche Bank AG Singapore.
He graduated cum laude in physics from the National Institute of Physics, where he studied the topology and causality of space-time. His interest in quantum computing was developed from his training in physics and computer science. Everyone, thank you again for attending today's webinar entitled Quantum Computing Philippines. Are you ready for the future of computing? Let us once again welcome Mr. Corpus and Mr. Manangan. Observe proper decorum, and most of all, enjoy the lecture.
Hello, guys. Thank you very much for having me here. My name is Bobby Corpus. So I'm the president of One Quantum, which is a global community of quantum for quantum technology. And our mission here in the Philippines is really to make quantum computing, to make people aware about quantum computing, and to make it accessible to anyone who is interested in learning about quantum computing, and also introduce quantum computing as early as possible into our child's education. And the reason for that is we think that the people who will be able to create quantum computers with large number of qubits are probably already in the elementary school. So, we must, as much as possible, make them quantum natives by introducing quantum concepts to them. Okay, so now I will now share my screen, and so let's start with the presentation. So I hope you can see my screen. Okay, so
Yes, po, sir. Clear po.
yeah, thank you. So together with me is Asher Manangan. So this will be a two-part presentation. One will be more of the theoretical stuff, and the other one, which will be presented by Asher, is going to be how do you actually program a quantum computer. Yeah, so prerequisites. So my goal is hopefully to be able to make you understand what quantum computing is. So I will assume that you don't have a background in quantum computing, but quantum computing is not easy. It's a totally different kind of paradigm, and that's why it's very important that we learn it as soon as possible. I mean, as early as now. Okay, so that's why it's not easy, but at least I would expect that you would be able to follow some basic algebraic manipulation. So we'll just cover enough theory, and then we'll talk about what qubit is, and then what a quantum gates, and how do you create circuits out of gates and qubits, and then I'll show you a bit of coding in a quantum computing framework called IBM QISKit. So what we'll not cover here is the implementation of quantum computers. That's a totally different kind of subject, and it's actually more complex than what we'll cover. Okay, so what's all this excitement about quantum computing? So this one is the poster child of quantum computing. Without this, I don't think people would be interested in quantum computing. So in the early 90s, it was shown by a guy named Peter Shor that if we have a quantum computer, this is how you crack the RSA and the elliptic curve cryptography. So what is RSA? What is elliptic curve cryptography? So these are the kinds of crypto systems that we are using whenever we go online. Okay, so for example, if you go to Amazon, it will immediately encrypt your session with them via HTTPS. And if you buy something, for example, from Lazada, it's already default that the transaction is encrypted. Otherwise, a third party will be able to steal your credentials and do the transaction on your behalf. So
Hello, Sir Bobby.
yes.
Excuse me, sir. Are you sharing, sir, the correct screen, sir? Because, sir, we're seeing here is the Balena Cloud.
Oh, sorry.
Yes, sir. Yes, sir.
Oh, sorry. Okay, let me stop. Thank you for that feedback. I thought I was sharing the correct screen. Okay, let me share it again.
Sure, sir. Thank you.
Yeah, I don't know why I went to the blind. Okay. Uh, yeah, it only shows that I'm a programmer as well. Okay, so can you see now the correct screen?
Yes, po, sir.
Okay, so you should see my name there and Asher's name. Okay, so I was already so let's repeat. So these are the assumptions which I already covered earlier, and these are what we are going to cover today, and what we are not going to cover. So I was actually in this slide when I was talking about the cryptography. So quantum computing can theoretically decrypt these crypto systems, and these are the crypto systems that we are using at the moment ubiquitously, as in everything that we do is online, that is supposed to be secure, are secured by these two, at least these two technologies. Okay, so RSA used when you are using a powerful enough computer, and elliptic curve is used when you are using, for example, a low power device like your cell phone. Okay, so RSA is based on the hardness of factoring a very big number. So imagine a number such as 2 raised to the 2048, okay, the 2048-bit encryption, okay? So according to research, it takes about 300 trillion years to decrypt such encryption, which means we are quite confident, okay, so at this point that no one is going to steal our credentials, okay. And this one here is elliptic curve cryptography. This one is a very powerful cryptography which is based on the mathematics defined on what is known as the elliptic curve, the one that you see here. Okay? So that's the elliptic curve. And this one here is the base point. So select any point. Well, select a well-defined point in the elliptic curve, like for example, this one here, and then add it to himself. So in elliptic curve cryptography, we define mathematics on top of the curve, so that when you add a point that is lying on the curve, you get another point in the curve, okay? So it can be different points, or it can be the same point, okay? So for example, in this one here, this is the same point. Okay, given this point, we add it to itself, it will give you this point number 2. Okay, if you add it again, it will give you point number 3 here, which is not seen. It's outside the this rectangle here. And then if you add it again, you'll get this point. Okay, and then add again, you'll get point number 5. So this point number 5 is called the public key. Okay, so this is the one which we send to someone who wants to not only send, but actually we advertise this to the whole world so that anyone who would like to send a message to us, they would just use the public key in order to encrypt our messages using elliptic curve. Now, in order for an attacker to be able to decrypt the elliptic curve encryption, they should be able to solve for this exponent here. Okay, this EA. Now, here the graph that you see here is a plot of b raised to the 5. Okay, so b added to itself 5 times. Okay, so to solve for the exponent, which is 5, is a very hard problem. However, it turns out that these two different crypto systems are in when you take a look at them abstractly, they actually are an instance of the same problem, and that's why the Shor's algorithm is able to decrypt them. Okay, so this is the reason why research in quantum computing has really flourished, because imagine if a quantum computer can already decrypt these crypto systems, then that's a big problem for all of us right now. Fortunately, we only have we're not quite there yet. Okay, so the most number of qubits right now, from what I know, is about less than 200 qubits. Okay, and in order to decrypt something like this, we need about 1 billion qubits. So that's the engineering challenge. In order to create a quantum computer, you need to be able to scale it to billions of qubits. So this is one of the first interesting things in quantum computing. Okay, quantum key distribution. So if you want to for example, communicate with me, there are 2 ways we can communicate. Okay, so one is the public key infrastructure, and the other one is using the symmetric key. Now, the symmetric key is very nice because it's a very fast kind of encryption. So, in order for us to conserve computing power, what we do is come up with a symmetric key and then send it to another person. For example, there are 2 characters whenever you talk about security, there are at least 2 characters. Okay, so one is Alice and the other one is Bob, and then there's a third one whose name is Eve, which stands for eavesdropper. So, for example, if Alice wants to communicate with Bob the symmetric key that they want to agree in order to encrypt their messages, what Alice will do is she will use either RSA or elliptic curve. Okay, so because that's what we have right now. Unfortunately, because theoretically a quantum computer can already decrypt this kind of crypto systems, then we need to find another way in order to send our symmetric key. And And the good thing is we can use quantum key distribution in order to do that. And thanks to the collapse of the wave function and entanglement, that is possible. It's now possible using quantum key distribution to determine if someone like Eve is listening to our messages. Because whenever Eve listens to our messages, the qubits will be destroyed, and you can determine that someone is reading your messages. So that's for quantum key distribution. So quantum computing is also used in optimization. So nature is is really awesome because for example, imagine you have water in the mountain. Okay, so that is not actually the proper place for water. Okay, so ultimately the water that is in the mountain will find its way towards the sea, and the reason for that is nature tends to economize on energy. Okay, so nature tends to economize on energy, and the energy level, or the minimum energy that water can attain is when it is in the sea level. Okay, which means that the distance between the height of water is zero. Okay, it's sea level. So that's what you see in nature. And another example is imagine you have a ferromagnetic material, no? And then you heat this material, and what will happen is that this material, they're composed of molecules, no, and atoms, and these atoms, they have what is known as a spin. Okay, so the electron spin. When you heat this material, what will happen is that the direction of the spins, they become random. Okay, so they become random. However, when you cool it down slowly, okay, imagine cooling down iron slowly, what will happen is that the molecules, they will tend to align their spins in such a way as to minimize the total energy. Okay, so imagine being able to utilize that kind of in other words, nature is always optimizing. Okay, so nature is always optimizing. Now, what happens if you actually harness that kind of behavior of nature? Okay, if you have a problem, what happens if you map your problem into some quantum system and let that quantum system optimize the energy naturally? Okay, it just occurs naturally, and then when it reaches the minimum energy, you can then get your answer. Okay, so that's what's happening in quantum computing as applied to optimization. So that one is called quantum annealing. Okay, so this is how you do it, no? So you have this instance of a problem. This one is actually an instance of a traveling salesman problem. And then what you do is you map this to what is known as the this is a very important term, okay, which I hope that you can remember, no? This is called the Hamiltonian. So the Hamiltonian is also known as the energy of the system. So you map your problem into the energy of the system. And because you know that the energy will be minimized, okay, once the minimum energy is attained, what will happen is that you will actually, this energy will correspond to what is known as an eigenvector, okay, which is the configuration of the spins or of the atoms, so that the energy of the total system is minimum. Okay, so when you say configuration, it's how they arrange themselves, no? Like this one here. And then once you get the eigenvector, this is actually each each variable here has a value of 0 or 1. No? It's zero. Zero means it's the spin is in one direction, and 1 means the spin is in the other direction, opposite direction. Now this one becomes the solution to your problem. In this case, the traveling salesman. Okay, so let's dig one level down. Okay, this one here. Okay, so how do you program quantum computer? Okay, so okay, guys. So having access to a quantum computer is one thing, but using it is an entirely different thing, no? So it's possible that you have a computer, but you allow the monkey to use the computer, right? Okay, so even if you have a computer and then you allow a monkey to use a computer, it will not produce the the sonnets of Shakespeare, no? So that's why another aspect of learning quantum computing is also knowing how to use it. And this is one of the things, no? How do you use quantum computer to solve your traveling salesman problem? Okay, so here, what you do is you map this, okay, into a route. No, so every route here is represented by this matrix. No, so for example, the route 2310. So it means that at the yeah. So for example, 2 here is in the first position. Okay, when we say first position, it's index 0. Okay, and then what's in the second position is 3. Okay, because 3 here means it's the value here is 1, no? And then after that 1, the value is in this column is 1, and then 0, the value in the third column is 1. So that's how you represent a vector, no? A vector or a route in traveling salesman. And then what you do is you unpack it into a vector, and then apply the constraints, and then compute the cost function. No? This one is the cost function of your traveling salesman. And then you map it into your quantum computer using what is known as the Ising model. No? And then here, this is the quantum mechanical equation of the energy. No? So H here is the Hamiltonian, and then K here is the value of the energy when you measure the system. No? So when your system evolves, no? So ultimately, so imagine that your system is in a state where it is all of the spins are random, no? And then you cool it down. What will happen is that it will attain a configuration so that the energy becomes minimum. And then once the minimum energy is attained, no, you measure this, and then you will get this the value of this this vector here called psi, no? And this is nothing but the solution to your problem. Okay, so that's how we can apply quantum computing to optimization. Now, but there's already algorithms that can do this, right? Like for example, in classical computing, we have what is known as the simulated annealing, no? So this is an example, no? So if you have a an algorithm called simulated annealing. This algorithm, what it does is also find the minimum, no? But sometimes the minimum, there are so many local minima, no? So how do you go from, and it's possible for you to be trapped, no? If your algorithm is not good enough, it's possible for you to be trapped in a local minima, no? So if you're here in the local minima, what happens to simulated annealing is that it will climb this hill, okay? It will climb this hill. This looks like the hill, no? It will climb this hill and then go to another minima, no? But in quantum computing, the technology is different, no? Because what it does is there is such a concept, there is such a phenomena in the quantum world, which is called tunneling, no? So tunneling, what it does is it will tunnel through this through the different kinds of minima, okay, until you get the minima of the global minima, okay, of your problem. So this one is hill climbing. This one is quantum tunneling, okay. And now that I have brought up the subject of quantum tunneling, no? So and the reason why, you know, if you have heard of Moore's law, no? So we are already in the we are already reaching the limit of how much transistors we can pack in a given unit area, no? And the reason for that is, you know, transistors, they are nothing but gates, no? They switch on and off, no? If you switch on, electrons will flow, no? And if you switch off, electrons will not flow, no? However, if your gate, no? If your gate, the one that stops the electron, is approaching 1 nanometer, no? What will happen is that the electron will not anymore be stopped, no? It will tunnel, it will go to the barrier, and that's why we cannot have we cannot create a transistor anymore of that size, no? And that's why quantum computing now becomes very important, no? Because quantum tunneling is a staple, no? We need quantum tunneling in quantum computing, no? We need it to be able to solve problems, no? But quantum tunneling is a problem in classical computing, like creation of integrated circuits, no? Because quantum tunneling, we cannot anymore make our transistors smaller, no? So that was just an aside. Okay, now this one is very interesting, no? So guys, no, so I think all of us here are in IT, no, and I'm also a hiring manager, no. So when I hire, let me give you a tip, no. So there are so many languages already, so many languages available, no, for anyone to use, no. There's Java, C++, no. There's Go, there's Rust, and so many languages, no, and .NET, no. And then, so if I have to interview a programmer, no, and for example, I have to interview a programmer to do some .NET, no, and however, I'm not really very good at .NET, no. I know the concepts, but I'm not a .NET programmer, no. So what do? I actually tend to go to abstract my questions, no, because I know anyone with sufficient experience can learn a language in a few days, no. For example, Python, no. Python, you can learn Python in a day, no. Go, you can learn Go in 5 days, no. So language doesn't matter for me as a hiring manager, no? What I'm looking for is someone who actually knows his algorithms, no? So I tend to ask them this kind of questions, no? Like, for example, I have a imagine, no? So there is a board exam, no? And then the result of board exam uh, is already released, no? However, is the thing, no? It's given in a pieces of paper, no? Piece of paper. And that paper contains for example, a name and a and name and whether the person passed or failed, no? So, and what happens if these pieces of paper are just left on the floor, no, in the mountain, no? So, and then you were the one who were asked by your manager, okay, if anyone comes here and asks for their if they pass or failed, no, you just search for their name there in that pile of pieces of paper, and that's it. You tell them they're pass or fail, no? So if you're a programmer, what would you do in order to make your life efficient, no? So the answer to that is first you sort it, no, and then you apply your binary search, no, in order to search, no. Well, in quantum computing, quantum computers are very good at finding things, no. So here I have here an example, no. Suppose you have a telephone directory, no, and of course, as a telephone directory, the arrangement of the names are in alphabetical order, no? And then suppose I want to ask for what's the telephone number of Asher, no? So it's very easy, no? In the worst case, it will, if I have a telephone number with, if I have a telephone directory with 1 million entries, no? In the worst case, it will only take me about 19 comparisons, or 19 flips of the pages in order to find Asher's name, no? But what happens, now here's the interesting part, no? What happens if you were given a number and then I'll ask you, what's the name? What's the name corresponding to that number? However, assume that your telephone directory doesn't have that reverse mapping, no? What will you do, no? So what you'll do is you will have to really take a look at each and every entry of the telephone directory until you find the number that you're looking for. Okay, so you take a look at all these numbers, no? At the right side, 817, 823, 966, okay? And then, for example, if you're looking for 966, oh, that corresponds to Albert. Now, it would be unfortunate or you will be unlucky, no, if the number that you're looking for is actually in the last entry, no, and you would have to iterate through all million entries, no, before you can find it. But with quantum computer, it only takes square root of n. Okay, square root of n iterations, no, or comparisons in order to find your number. And this is the next popular algorithm in quantum computing. This is called Grover's search algorithm, no? And what is really interesting about Grover's search algorithm, no, it's not the same as, you know, you program your bubble, you know, your classical search, no? It's different. Here, we are talking about, in the quantum world, we are now talking about what is known as vectors in Hilbert space, no? So remember those, no? Vectors, Hilbert space. These are the things that a quantum native would know, okay? So for example, in the future, your kids will just be very conversant about these two concepts, no? So how does Grover search? No, let me just give you a picture of how it works. No, it's different. No, and it's quite exciting. So this is the entry that you are trying to search is represented by the vector A. No, vector A, and this is the vector that you begin with. No, in order for you to search for A, what you do is to rotate your vector, this vector, square root of n times, no, where n is the number of entries, no, square root of n times, and then once you are able to rotate it in, for example, if you have 1,000,000 entries, you rotate it 1,000 times, no, and once you do the 1,000 rotation, you are already, there's a high probability for you, which is, you can see here, no? There's a high probability for you that whenever you measure the system, you will get the correct answer, okay? So probably you are now confused, no? What is this measurement, no? So I will tell you that later, no? But whenever you do operate a quantum computer, no? At the end of every algorithm is measurement, no? When you measure it, that's the time, that's the time you want to ask it, what's the answer? So now if you measure it and for example, this one, the probability of getting a 110 is very high, like 90.945 probability, no? So which means that most of the time you will get this answer, okay? So that's the thing about quantum computer, no? It's not like 1 + 1 = 2, no? It's 1 + 1 equals, it can be 1, it can be 2, it can be, it's probabilistic. That's why it's a different kind of mindset, no? And that's why it's so interesting. And that's why I'd like you to explore it, no? Okay. And quantum computing is also used in machine learning, no? Artificial intelligence. So if you are a practitioner of machine learning and artificial intelligence, no, you will you will know that at the heart of every machine learning or artificial intelligence algorithm is a cost function, no? And quantum computers are very good at optimizing a function, no? Especially here, you can also use the Grover's algorithm to find the minimum or the maximum of a function. And the thing about the Grover's algorithm, no, which is different from other algorithms like gradient descent, no. Well, gradient descent, if that's a standard way for you to optimize a function, no? But it has some requirements, no? Like for example, your function must be convex, no? So it must be convex. But the thing about not all optimization problems, no, are the same, no? So sometimes your function to optimize might not be convex, no? And how do you deal with that, no? And the good thing, and if you are able to deal with that, this means that your algorithm for machine learning and AI, no, they tend to be able to generalize properly, no, and then they tend to minimize noise and outliers, no. So that's the purpose of that's the application of quantum computing in AI, no? And this one here is a table. So as you can see, we already have some so for these are the algorithms, no, used in machine learning, no? And then there's already quantum versions of these algorithms. And here you can see when you see that it's a quadratic speed up, it means it must be using Grover, no? And exponential speed up, when it's exponential speed up, it means it's really very, very fast, no? So imagine, no? Imagine na lang, no? 2 to the 50 is about 1 petabyte, no? And that's a very big number, no? Imagine you are going to you have an algorithm that has that needs that will take an input of 1 petabyte worth of data. Imagine that. And then that's a very large number. However, if your algorithm is exponential, what does that mean? If it's exponential, it means that you get the logarithm, no? Logarithm of base 2 of 2 to the 50. You only need 50 iterations, no? It's very fast, no? So this is this table is, you can see that we already have versions of quantum versions, no? Of machine learning algorithms. Okay. And then this is really very interesting because quantum systems are very hard, extremely hard to simulate. Okay, so let me give you that example again. No? So imagine you have a system, okay, with 50 atoms. Imagine, and then you want to simulate that. Okay, at the minimum, you need about 2 to the 50 worth of memory RAM in order to store the various configuration, the various positions of your atoms. But 2 to the 50 is 1 petabyte. You don't have a computer that has 1 petabyte of memory, right? So it's so hard to simulate quantum systems. But with a quantum computer, you only need 50 qubits to simulate those 50 atoms. No? So that's, imagine 2 to the 50 versus 50. That's called an exponential speed up. Okay. And the example that I'm giving you here, this is about protein folding. No, protein folding is very important. No, problem. That's why there is an organization called folding.org that is just dedicated to computing the folding of protein. You know why it's very important? It's because protein that does not fold properly will give you diseases like mad cow disease, Parkinson's disease, okay, Alzheimer's disease. Right? These are diseases that arise because protein, they didn't fold properly, no? And so we want to be able to understand how protein folds properly, and that's why we need to be able to simulate protein folding, and quantum computer can help you with that simulation. Okay. Okay, so I will now give you some use cases where quantum computing is going to be applied. No? So, number one, healthcare. In healthcare, we want to be able to come up with better drugs, no, or with better medicine. But in order to be able to do it accurately, you need simulation, no? So you simulate using supercomputer, but like I said, it's what if the number of components in your quantum system is large, no? Or if you have a molecule that you want to simulate with large numbers of components, no? Uh, it's it's very prohibited. It's very it takes a long time to simulate that, no? So that's why we need quantum computing, no? So simulation of chemical reaction also, no? In quantum chemistry, you need a quantum computer to simulate it efficiently, no? So all of this, no? I already mentioned protein folding. Um, so here in the making of making more money, no? So quantum computing can help us. So for example, if you want to, if you have lots of stocks, no? And you want to diversify your stocks, and you want to minimize the risk, no? How would you go about it, no? So it's called portfolio optimization. But we know that portfolio optimization is nothing but a combinatorial optimization, right? So it's it's one of the strengths of quantum computing. So you can apply quantum computing there, no? In fraud detection, no? The quantum computing data modeling capabilities, no? They are expected to prove superior in finding patterns and performing classifications. In quantum risk analysis, no? So you're able to come up with this model, no? And then you want to be able to see if this model is able to when you apply it, no? What are the risks of you applying this model, no? So the quantum computing data processing capabilities will speed up the risk scenarios simulations, no? With higher precision. No, blockchain, no? So everybody talks about blockchain. Okay, so Bitcoin, no? Eh, but the people right now, no, they are already cognizant, no? People who are in this technology, they are cognizant that one of these days, no, their the encryption that they're using, no, which is by default elliptic curve cryptography, no, can be cracked already by the quantum computer, no. So that's why there is now an initiative, no, in order to come up with new encryptions that are quantum resistant, no? They call this post-quantum cryptography, no? So so that's the application of quantum computing, no? In blockchain, cryptocurrency, and also in cybersecurity, you know, quantum key distribution, which I explained earlier, no? And these are machine learning algorithms, no? That's already I showed you earlier. That's already has some quantum alternatives, no? So you can apply it to these use cases in machine learning. And so in logistics, these two companies, no, they are already experimenting on quantum computing. Okay, so for example, DHL, they want to so DHL they own they own airplanes now. So in order to maximize or to optimize, no, routing between of their airplanes, no, in different cities, no, they are already investigating on how to use a quantum computer. Volkswagen, no, it's they also experimented on how in how to optimize the routes, no, on the street, no, in order to make deliveries delivery vehicles make more stops in less time, no? And Airbus, no, so in manufacturing and design, no, Airbus is also experimenting. In fact, Airbus has had a hackathon, no, on quantum computing, no? So they are using it to design airplane wings, no? So the most efficient way to design wings of the airplane, and the Daimler and Samsung are using quantum computing, to build better batteries, no? So this is where you apply quantum computing to simulation, no? And this one here, no? uh, in the semiconductor industries, no? You can apply quantum computing as well, no? To identify the shortest wiring, no? Of your billions of transistors, no? And of course, you need to verify. You need to be able to verify, whether that your design is correct, no? So quantum computing uh, is also capable of solving SAT problems, no? So this Boolean satisfiability problems. And in agriculture, so quantum computing is also very it's also applicable agriculture, no? So the main problem of agriculture is how do we make more food, no? And the key to that is fertilizer. So to produce fertilizer efficiently, how do you use quantum computing to do that, to solve that problem, no? So you apply simulation, no? In fact, here in number 3, this is really interesting because every day the bacteria at the foot of the trees, no, they produce ammonia quite effortlessly, no. With what I mean is that they only expend minimum energy in order to produce ammonia, but they use a uh, a molecule called nitrogenase, which we don't understand, no? And in order to simulate this, of course, you can simulate it with a supercomputer, no? But well, I mean, it says here that it's beyond ability of a supercomputer to simulate, but maybe it might be within reach when we have already a quantum computer with sufficient power. Okay. Okay, now that I have told you about the importance of quantum computing, where we can apply it. So the next question is, how do I do it? Okay. So when I say how do I do it, I'm placing myself in the shoes of a programmer, no? So if I was a programmer, how would I program a quantum computer? So here we are going to talk about qubits, and then gates that operate on qubits, and then circuits, which are a combination of gates and qubits, and then finally measurement, no? So you want to know the answer, no? So you have to measure. Okay. So before that, let me introduce you to the most beautiful experiment in physics, no? This was voted the most beautiful experiment in physics, no? It's called the double slit experiment, no? So double slit experiment demonstrates the quantum mechanical effect of a phenomenon called superposition. Okay, so probably you have heard of Schrodinger's cat, right? So imagine you have a double slit. You have a wall with 2 slits. Okay, 2 slits. Butas, no? Slits. And then you fire electrons into that slit. And here at the back of your wall is a detector, no? And it will detect which location the electron was detected. Okay, so imagine first that you close this slit here. Okay, let's say that this is slit 0. Okay, and this is slit 1. Okay, sorry. There's actually a label here, 1 and 2. No, so slit 1 and slit 2. You close first slit 2, and then you fire your electron. What will happen is that you will get this profile, no, of it's a probability distribution. No? So when you see that this one here is a maximum, this means that a lot of electrons uh, were captured here, no, and then in here almost 0, no, it tends to 0, okay, and it decreases, no. Now, what happens if you close the slit 1 and then open slit 2? You will get this, no? The same pattern as slit 1. However, if you open both of them, you will get this very peculiar pattern, no? And this pattern looks like the pattern when you have water waves, no? Water waves that go through 2 slits. They will look like this as well, no? Using water interfere. The water waves interfere with each other, no? At the point where they uh, where they interfere negatively, you have this one here, no? And at the point where they interfere positively, the waves they grow, no? They grow bigger. And it's the same here, no? With electrons, you know, you fire electrons into this wall. Now, the thing is, even if you only fire one electron, what happens is that they have demonstrated that the electron is able to interfere with itself. Okay? So what does that mean? Electron able to interfere with itself. And you fired only one electron. Okay? So we know from common sense that the electron is either going through this slit or this slit. Okay? There's only one electron, no? So pick one of these holes here, no? For the electron to go through. But the behavior of quantum systems, no, when things are very small, no, in the quantum realm, no, they behave differently in such a way that when you fire one electron, the electron produces this interference pattern. So what does that mean? It means that the electron went through both slits, no? Or the electron behaved like a wave, and it's able to interfere with itself. And why am I telling you this? It's because this is the behavior of a qubit. Okay? So a qubit is able to be in 2 different states at the same time, no? However, when you measure a qubit, it will give you a definite value. Okay? So, which means that you do your computation while the electron is in superposition, no? While the electron is in 2 different states, you do your computation, no? You extract your square root, no? You compute your Fourier transform, and then measure. Okay, so that's the importance of this page, no? Now, so let's now go to so what you're seeing here is called a quantum circuit, no? A quantum circuit is composed of qubits, no? And then you group qubits into different groups, no? So one qubit here, which I call the input qubit, no? And the other qubit, I call the other group of qubits, I call the output register. So this one is the input register. and this one is the output register. And then when you measure your quantum system, no, to get the answer, you need to store it somewhere, no? So you need to store it in a classical bit. Okay, this one here is the classical bit. So measure this thing that you see here, which is like a measuring device. This is the icon for a measuring, no? So you attach your measuring device to a qubit, no? And then whatever is the answer, you write it into the classical bit. And this one here that you see here, this line, horizontal lines, these are called wires, no? In the wires, you attach what is known as the gates, no? The gates are those functions, no? Or those things that those are the things that transform your qubits, no? In different ways, no? So you attach it here, and you can have so the direction of time is from left to right, no? So which means if you have a gate that is located here and a gate that is located here, it means that you first apply the first gate here and then apply the second gate. Okay, so that's the direction of time. And this one is the definition of a qubit. So what's a qubit? A qubit is an abstraction, no, of a quantum mechanical system, of a two-level quantum mechanical system. So when you say two-level, it has two states, no? So in this case, it has zero state and the one state. And the one that you see here, this is very, very, what you call this, curious notation, no? So guys, do not be afraid of notations, no? They are just things that stand for something, no? So this one here is called a bra. Okay, so in quantum mechanics, vectors are called bra and ket. No? So the bra vectors and ket vectors. And it was invented by a genius, no? By the name of Paul Adrian Maurice Dirac, no? So this guy is really genius. He doesn't speak much, no? He's a very silent guy. That's why they say one Dirac is like one word per year. So this guy is very silent, but very intelligent, no? So he's the one of the inventors of quantum mechanics. No? So PAM Dirac, no? He's one of my idols, and he was the one who invented this this notation. No? So this is called a bra. Sorry, a ket vector, and the number that you see here is a label. No, so this means that the ket vector is at zero state, and the ket vector here is in the one state. No, zero usually is ground state. One is the excited state. Okay, and a qubit is, so a qubit can be in a superposition. Okay, it can be in a superposition. It can be in a combination of these two states. No, imagine in classical computing. No, like for example, what we are using right now. No, which is the ordinary computer. No, it has it's using bits. No, a bit has a value of 0 or 1. Okay, but not both. A qubit can have a value of 0, can have a value of 1, or in between. Okay, so that's called superposition. That's why we represent a qubit like this. No, it's a superposition. No, it's a sum of these two vectors. No, it's a combination, and the letters A and B here, they stand for complex numbers. No. No, it turns out that complex numbers are very important in the real world, especially in quantum computing. No? So imagine you're using complex numbers and then you're only reading the real value and then throwing the imaginary value. But in quantum computing, no, you don't throw your imaginary value, no? Complex numbers are fundamental to the operation of the universe. That's why, no, you cannot have a quantum theory without complex numbers. So A and B here are complex numbers, and the modulus, no. So when you say the modulus of the length or when you say modulus, it's the what you call it? It's the so when you have a complex number, no, when you take its magnitude, okay, and when you take its magnitude, that's called the modulus, no? And then here, you take the magnitude of A, square it, and then B, square it, should sum to 1, no? In other words, this one is, and the reason for this is because these complex numbers are probability amplitudes, no? So another very important concept in quantum computing is called measurement, no? So you have a qubit, no? In superposition 1, 0. However, they are only in superposition as long as you don't observe them. Okay? So mahihain sila, no? Para silang KitKat, no? It's like KitKat, no? Whenever you observe, the panda doesn't go out of the cave, no? Whenever you observe, panda doesn't go out of the cave, no? But when you observe, the panda goes. But when you don't observe, that's when the time the panda goes out of the cave and dances, no? I'm not sure if you've seen that advertisement of Kit Kat, no? So in quantum computing, no, in quantum computing systems, whenever your qubits can be in a superposition as long as you don't observe them. So that's where when they are in superposition, that's the time you do your computation. Okay, and of course, the end result of computation is you want to know the answer, right? So that's the time you measure it. So imagine you have this after taking, for example, the square root, no? The state of your qubit is like this, and then you want to know, is my qubit, what's the value of my qubit, no? When you measure it, what will happen is that it will collapse into a state. Pick one, no? Pick one. It's either 0 or 1, no? So here in the measurement, when you measure, it's not anymore both, no? It can only be 1, okay? But the question is, which one will most likely occur, no? So the numbers here, A and B, they give you the if you square them, no? If you square their magnitude like this, it will give you the probability of that occurring, no? So for example, if this one here is 0.8 and this is 0.2, okay? So most of the time you will get this answer A, okay? And that's actually in quantum computing, the answer that is the state that will occur the most whenever you measure is the answer to your question. Okay, so that's quantum. Yeah, so that's measurement, no? So let me show you now. How do you program a simple, very simple quantum circuit? Okay, so this one here is a very simple program. No? This one is written in Python, and This one is written in Python, and it's using a framework called QIS-Kit, and the UI that you see here is called Jupyter. No? It's a Jupyter notebook. So to create a quantum circuits, it's quite easy, you know, especially if you're very much used to it. No? So here in this line, I'm creating a quantum register, no? Composed of 2 qubits. And then here I'm creating a classical register composed of 2 qubits. And then I'm going to create a circuit out of them. Okay, so this is where the quantum circuit line is. And then you put some measurement. Okay, you measure it. And then we draw. Okay, let's take a look at what happens. Huh? How does it look like? Okay, so this is your very basic quantum circuit, no? It does nothing. Okay, so by by default, the qubits are initialized to 0. Okay, so they're in the ground state. So if they are initialized to 0 and you measure them, what will happen is that you will get 0. Okay, so let me show you a simulation of the measurement. Let's run the circuit. And this is what you get, no? A probability distribution. So in quantum computing, you will get your answer is a probability distribution. And the one with the highest probability is your answer. Okay? So in this one here, it's very simple, no? We only have one outcome, which is 0, 0, and the probability is 1. Okay, so and the reason for that is this one is initialized to 0, no? Okay, now what happens if I initialize this to 1? What will I do, no? So what you do is like this, no? You see that okay, I'm getting ahead of myself, no? So let me just do that later, no? Okay, so let's go back to our presentation. Okay, now so you have qubits now. In order to influence, now in order to do computing in quantum computing, you need what is known as the gates, no? Or these are also called operators, no? So I'm going to introduce you to 3 operators, and these are already very useful operators, no? And so that you'll know the concept. So one of the operators or gates that we use is the NOT gate. NOT gate is very familiar, no, to us, no, especially if you're a programmer or in the electronics industry, no. NOT gate is the one which negates the value of your qubit, no. So for example, if the value of your qubit is 0, what it does, it transforms it into 1, and vice versa. Okay, and so now that I know the NOT gate, how can I initialize this to 1? It's very easy, you know. You can just do this. You see that X, and then I put the index of the qubit now. The name of the qubit of the quantum register here is Q in, and I'm interested in the 0th qubit, no? So if I do that, if I run this, so this one is this is now initialized to 1. Okay, so when I measure this, I should get 1, 0, no, 1, 0. So let me measure it. All right. Okay, 1, 0. Okay, 1, 0. Well, actually, you read it as 0, 1. No? So dito pala 0, 1. Okay. Okay, so let's go to the next gate, no? Which is called the um, it's a gate that allows you to do if uh, if like condition, no? So this one is a 2-qubit system, no? So which means that it needs 2 qubits for it to operate. Okay, the first qubit, the one here, this is called the control qubit, and then you have a target qubit. Okay, so the control qubit is the one which controls what will happen to the target, no? And the rule is simple, no? If the control qubit is 0, don't do anything here. Okay, don't do anything. However, if the control qubit is 1, whatever is the value here, you flip it, no? So in other words, this is the truth table, no? So if it's 0 and the value of your y is 0, 1, take a look, huh? It's the same. Okay. However, if the value of the control qubit is 1, what will happen to the 0 here? It becomes 1. Okay. And what will happen to the 1? It becomes 0. No? And this is how this is how you visualize it in a circuit, no? Okay. So if we go back here, no? So it's if you want to do a control, no? Control between this one and this one, what you do is, you see that CX, it's called CX, no? The control qubit is Q in, and the target qubit is Q1, no? Okay, so let's draw it, no? Okay, take a look, okay? So whenever this one is 1, it will flip this value, okay? Now, since we already initialized this to 1, what will happen is that the 0 here becomes 1, and the value of your circuit is 1, 1. Okay, so let's do that. No? Let's show that by doing a simulation. No? Okay, it's 1, 1. Okay, so that's a very basic quantum circuit. Huh? And finally, the Hadamard gate. No? Well, finally, because I'm going to introduce you to only 3. No? There's actually a lot of gates, no? But this is very, very useful. Hadamard is the unsung hero of quantum computing. No? Without Hadamard gate, you wouldn't have your familiar superposition. No? So what happens that the Hadamard, when you apply it to a qubit that is in the value 0, it will put it in this state. Okay, a superposition between 0 and 1 with this this one here is positive. But if your qubit is in the state 1, it will give you this superposition state, no? And the square root of 2 here is there because we want to make sure that when you measure the probability, the sum of this the terms here will be equal to 1. Okay, so let's take a look at the Hadamard. No? Yeah, so this one here is the Hadamard. No, so in here I am going to apply a Hadamard gate to the 0th qubit, and I'm going to employ a Hadamard gate in the first qubit, no, with the qubit in the index qubit, and then do a measurement, no, and then run it, no. So this is how it looks like, no, Hadamard. Now, why is Hadamard very important? No? Like I said, this is the one which gives your qubit in superposition. No? So how do you prove that? No? How do you show that? No? You run this. No? So what does it mean? No? Whenever you measure your qubit, it gives you these states. No, gives you 0, 0, 0, 1, 1, 0, 1, 1. No, with almost the same probability. In other words, your qubit is now in superposition. Okay. So you can also show that mathematically, no? So uh, you can do quantum computing, no? Just by doing this mathematics, no? So in here, you know this one. This is the given, and this is you apply Hadamard to both qubits. What will happen? Okay, so this one is equal to this one. This is the one. Okay, and this one here, the same thing, no? And then you multiply them, no? And the curious thing about this multiplication is that it's non-commutative, no? So you cannot interchange, no, the arrangement, no? So you have your 0 0 and then 0 1, no? And then 1 0 and then 1 1. And then square root of 2 times square root of 2. That's 2. And then here's the curious thing, no? 0 0 0 1 1 0 1 1 are nothing but binary expansions of the decimal representation, no, of 0 1 2 3. So which means we can actually write this in compact notation like this, no? So this one is your superposition of states. Okay. So the Hadamard is the one which gives us the familiar superposition. No? Okay. Do we still have time for Asher? Guys?
Yes po, sir. Meron pa
Okay.
naman akong time.
Yeah, I still have probably 3 more slides, and then we will go to Asher.
Okay,
Sir,
po,
no
sir.
problem.
Okay, so now this one will show you the power of quantum computing. This is called the Bernstein-Vazirani algorithm. No? So in this problem, you are given a black box function, okay, and that black box function, being a black box, no, it has an input and an output, no, and the input can be any number, no. For example, if you have 3 qubits, then the numbers can be 0 up to 7, no, because 3 qubits can represent 0 1 2 3 4 5 up to 7. Now the output is a number 0 or 1, no? So it will give you either 0 or 1, no? And further, you were told that the black box function has an unknown number, which how it works is like this, no? If you are given, if you give it a number x, what it will do is it will decompose this x into binary notation, and then there is a unknown number a, decompose it also into binary notation, and then do a dot product, no, a bitwise dot product. Now the problem here is, the problem that you are supposed to solve is compute for the unknown number a, no? So in classical computing, no, you need, if your number is if the number of bits of your number is n, you will need n iterations in order invocations of the function in order to determine the number. So if you have a 3-qubit number, no, so which is it's a number between 0 and 7, then you need 3 invocations of f of x in order to decipher what or compute the number a. And how do you do that? It's like this, no? I will craft a number so that it will give me, whenever I put this into the black box, it will give me a digit of A. So if I put it 2 to the 0, which is 1, it will give me this value. So by the way, our A here is assumed to be 101. Huh? If I put 2 to the 1, then it will give me this this number here, which is 0. And then if I give it 2 to the 2, which is 4, it will give me finally this number here. Okay, this number 1 here. So by doing that, I'm able to get 101, which is this one here. Okay. So imagine you have a billion. Your number is has a billion bits. No? Then you need 1 billion iterations in order for you to get the in order for you to compute for the number. However, in quantum computing, whatever is the length, no, whatever is the length, or whatever is the value of n, no, whatever is the length of your bits, you only need to invoke your function only once, no? Only once, no? So how do you do that, no? This is called the Bernstein-Vazirani algorithm, no? So the first thing you do is to first create your function, no? Create a function in terms of gates so that whenever you put these numbers, it will give you the correct answer, no? So for example, if I put number 7, so 7 is decomposed as 111. If I dot product it bitwise to the number A, so 1 times 1 is 1, 1 times 0 is 0, 1 times 1 is 1. Okay? So this one is 0, and you have 1 and 1 here, no? Now, if you add 1 and 1, XOR, you will get 0. Okay? XOR. 1, 1, XOR, 0. So, this circuit here actually is able to compute all of this, no? So as you can see, guys, no? This is how you program now in quantum computing, no? It's different kind of programming, no? It's called creating a circuit. So, for example here, if this is, if the value of the qubits here is 111, and we know this one to be the control not gate, no? So if this one is 1, and the initial value here is 0, what will happen is it will flip the qubit, the qubit value, and this becomes 1. Okay? So 0, naging 1. Okay? Now, since this is also 1, kasi yung number nga natin is 101, no? Sorry, 111, no? So 111. Since this one is 1, it will also flip the value here, and it will become 0, no? So which means f of 111 will give you 0. In fact, you can verify that this one is actually computed correctly, no? Everything here is computed by the circuit. Now, how does a quantum computer able to compute for the value A with just one invocation of the function? It's like this. Okay, so you create the circuit, and then when you measure it, you will get the value of A. Okay, so let me show you that now. So this one is the Bernstein-Vazirani program, no? So if you run this, okay, this will give you the circuit, no, that I showed you, which is this one here. Okay. Now, if you simulate it, this gives you the value 101, no? Which is our hidden number. Okay. As you can see, what happens here is that the Hadamards, they what the Hadamards did was to create a superposition of all possible inputs, no? So all possible inputs here, no? So for these 3 qubits, it gives the values 0 up to 7, no? And then all these possible inputs are then fed into this function. And it's called only once, no? And then after that, you get the Hadamard again. And that's how you get this answer 101. No? And it turns out that, so here, the numbers here, these are an illustration now, because the thing about quantum computing as well, no, is this circuit here can be translated into mathematics. No? And then once you translate this into mathematics, these are called the tensor product. No? One of the things that you need to familiarize yourself, no? The tensor product. And this one here is the, these are the control nut, no? So this is the control qubit, which is 1, and the target qubit, which is 0, no? So 1, 0. And then this one here, 3, 0, means this is your control qubit, and this is your target qubit. No? And the reason why it works is because it turns out that this circuit is equivalent to this circuit, no? This circuit is equivalent to this circuit, no? You can just show it as an exercise, no? And if we focus our attention to this circuit, if you initialize the Q out to be 1, what will happen is that all of this, the one with the plus, they will flip into the value 1, no? Like this. So if you apply the X, the value of the qubit from 0 becomes 1. And because this becomes 1, all of these that are attached to it, this one here, since this one is called 0, this becomes 1. Since nothing is attached here, it's still the same, 0. And the value here, 0, it gets flipped and it becomes 1. And this is nothing but your value A. Okay? And like I said, if you expand this, you will also end up with A. So what am I saying here? No, quantum computing is not an easy subject, no? But if you focus your mind into it, no, you will be able to understand it, no? The learning curve is quite high, no? It's quite high, the learning curve, no? But if you are really interested, no? We are here, no? One Quantum, at least locally, we are here as a community to help you in your journey in quantum computing. Yeah, so that's the end of my presentation, and I will now turn over to Asher in order to give you a little more things in the programming side. Asher?
Hello, Sir Bobby. Thank you very much for your
Okay, I'll stop sharing.
very nice talk. Okay, I will now share my screen. Okay, so I'm Asher, and I will be doing the demo session for how to program a quantum circuit. Now, let's try to program on a quantum computer. So before that, if you want to work along with us, you can click this link. So bit.ly 3EYDVXN. So when you are going to navigate into this link and then press enter, okay, you will be go into this site. It's a Google Collaboratory site. So this platform, this Google Collaboratory platform is owned by Google. And you know, we have like classical computers like your laptops or your phones right now, these devices sometimes lacks the resources. So for example, you wanted like to compute for a very compute intensive problem. What we can recommend is go to your Google account and try to search for Google Collaboratory. So Google Collaboratory is a platform where you can program and do your coding without much burden on your local machine. So you will be using a machine that is provided by Google. Okay, so once you've already into this workbook, so again, let me show this link. So once you've already in this workbook, let's try to explain first, okay, the first part, which is the quantum logic gates. So a quantum logic gate are the building blocks of quantum circuits. You know, like classical logic gates are for conventional circuit. So for example, in our classical circuit, right, we have like truth tables. We have like OR gate, we have AND gate, we have exclusive OR gate. At the same time, we have that same idea in a quantum circuit as well. The difference is we're gonna be using quantum circuits, and most of all, instead of working with bits, we're gonna be working with qubits. Okay. So for exercise 0, we'll be working up to exercise 7. Okay. So for exercise 0, what we can do is to import the required libraries. So what this libraries mean? So this library that you can see here, this code right here, is the libraries that we need in order for us to work with the quantum computing framework. So for this workbook, we're gonna be working with QIS-Kit. So this one, QIS-Kit. So QIS-Kit is a framework provided by IBM. So it's an open source framework that we can use to get started working with quantum programming. So to do that, let's just run this command. So let me close this for the moment. So let's just copy, if you, okay, so let's just run this command. So click run anyway. Okay, so it's now loading. So in the background, what it does, it's try to download this package. Okay, so later you will be seeing the progress of this one. Let's wait for the meantime. Because if we don't have this package, what will happen is we cannot work with the quantum programming. So let's see. So it says check. Okay. So now it's downloading the required dependencies. Okay. Let's wait for it to complete. Okay. Actually, there's a way for us to make this faster. The way to make it faster is of course uh, by some plan for Google Colab. Currently, we're using the free version, but for this workshop, we can uh, work with this one. So okay, successfully built, installing packages. Okay, okay, looks like it's already done. Now let's go to exercise 1. So there are 3 instructions here. Let's copy paste the code below, run the code to show the circuit, and let's modify the code. Before that, let's understand what is this code that we're gonna copy pasting. So this first 2 line, okay, will import the required libraries. So as you remember a while ago, we have installed the libraries that we need. So what we're gonna do is let's try to import it into our code so we can use the functionalities of that libraries. So we are importing the QIS kit SDK. It's a software development kit. And then let's start the quantum programming. So, okay, so let's try to create the input quantum register with 2 qubits. So to do that, we're just gonna define a variable. It can be anything you want. Then we have this function quantum register and the number of qubits that you're going to use, okay? And then let's create a classical register with 2 bits that will hold the result of the measurement. So again, you can name it any variable that you want. And then we use the classical register function and the number of the bits for your classical register. Then after that, we are gonna create, okay, the quantum circuit. So we have the variable QC, and then we have this function, no, the quantum circuit. So quantum circuit takes a number of qubits of your quantum register and your classical register. So these parameters, we have the quantum register and the classical register. So we pass it on our quantum circuit, and then this is a barrier. Okay, so now let's try to draw it. So to do that, copy, let's copy this code, and then let's paste it here. So let's run. Okay, it's running. Okay, okay. So as you can see, we have the two input quantum register, this qubit 0, qubit 0, index 1, and we have two classical bits, okay? Again, and for the third instruction, let's modify the code to create a circuit with an input register of 3 qubits and an output register of 1 qubit and a classical register of 3 qubits. So to do that, let's modify this one. So we need to have a quantum register of 3 qubits. Oh, okay, okay, here should I edit? 3 qubits, and then we need to have a classical register of 3 bits as well. Then the additional part is we're gonna define the the quantum output register. Create the output quantum register with 1 bit only. Okay. So to do that, let's just name our variable Q out and quantum register. Then, of course, we only need 1 qubit, so we have it there. Then we have our classical register. We change it to 3, and then we're going to pass the parameters to create our quantum circuit. So to do that, what we're gonna do is just to add our quantum output register. Okay. So let's try to run. As you can see, now we have the uh, 3 qubit input register, and we have 1 qubit output register and 3 classical bits. Great. Now let's work with the exercise number 2. Okay. So this one. So this function, the simulate function, okay, will going to simulate our quantum circuit. Actually, we are currently working with quantum programming on our classical machines. So this one is trying to simulate the behavior of quantum computers. So how is it possible? Because it's able to work with it, and because uh, we can work with it since we have only a small number of qubits that we are using. Okay. However, if our qubits becomes bigger, that's the time that our classical machines cannot cope up with it anymore. So we need a much more powerful computer, which is a quantum computer. Actually, we can do this directly on a quantum computer on IBM. It's also free. However, currently it will take a very long time since it's queued, so the operations will take a longer time. Anyway, what we're gonna do is just to copy this code, and then uh, let's run, copy the code to simulate the circuit. So let's click this one and then press run. Okay. And then let's simulate the current circuit by running the function. Then we pass the parameter, which is our quantum circuit. So let's click run, or rather here, much cleaner. Okay. So as you can see, it give us the result, which is 000. So as you remember, quantum input registers, or the quantum registers initialize the inputs to 0. That's why we have 00 here. Okay. Now let's work with exercise number 3. So this part is the part where it gets a little more interesting, since we will now be working with idea of superposition. So superposition is made possible through the gate known as the Hadamard gate. Okay. So what we can do, let's just try to run this code. Okay. So let's run this code. Okay. Okay. In this circuit. So let's copy paste the circuit we have a while ago. Then we will add that Hadamard gate in our circuit. So let's just copy paste it here first. Okay, so then type simulate. Okay, okay. Then we will be using the Hadamard gate onto the first input register. Okay, so let's place it here. Okay, then let's click run. As you can see, we now have probabilities of 0 and 1 occurring. Okay, so let me comment this one out. So you can see the drawing of the Hadamard gate. As you can see, a while ago, this is the only circuit that we have. We don't have a Hadamard gate yet. Then we apply the Hadamard gate on the first qubit. So this one is this one. Okay, great. Now, let's work with the exercise 4, which is superposition. Okay, so let's try to create this following circuit from scratch and try to simulate it. Okay, so to do that, let's try to, of course, have our first quantum input register, quantum quantum register. Then we need to have like two quantum register, and let's give it a name so it will be better to see. We have a label, it's much better to understand. And then let's have our classical register. So to do that, let's just type classical register. And then how many classical register we need? We have two. So we just pass number 2. And then the name, let's say the classical register name is C1. And then let's initialize our quantum circuit. So to do that, we have the function quantum register. And then we pass the registers, quantum circuit, I'm sorry, quantum circuit. Then we pass the required registers, which is QIN and the classical bit. And then after that, let's try to work by adding the two Hadamard gates. So to do that, let's type qc.h. Then the first qubit, let's add it the index 0, and the second qubit, which is on index 1. Okay. And after that, let's create a barrier to make things a little bit TD and clean. So barrier. So barrier doesn't do anything. It just visualization to make the circuit appear organized. Then after that, we're going to measure the first qubit and direct the measurement to the classical register. And we have the second qubit, and let's output it onto the our classical register. So to do that, let's work QC that measure. So measure is the function we need to use. So it takes the input register qubit register. So it's 0, and the classical qubit, the classical bit register, which is this one, which is also in 0. And QC measure, we were going to work with the second qubit and direct it to our second classical bit. And then let's try to draw it. QC.draw output MPL. Okay. So let's try to run. Okay, so we have an error output. That should be you. Okay. Okay, great. Now, as you can see, this circuit is the same as this circuit. And then, of course, let's not forget to simulate it. Okay, simulate QC. So let's try to simulate. So as you can see, we have all of the possible outcomes of 2 bits, right? We have one, which I mean, we have 0, 0, which is equivalent to 0. We have 0, 1, which is equivalent to 1. We have 1, 0, which is equivalent to 2, and we have 1, 1, which is equivalent to 3. So using the Hadamard gate, it makes all of the possible outcomes. Okay, so it makes all of the possible outcomes. Okay, down our inputs. So we have like 2 bits. Okay, so we have 0, 1, 2, and 3. Okay, so that's the magic of Hadamard gate doing superposition. Okay, so for exercise 5, okay, so we have what we call as a control NOT gate. Control NOT gate. So this is the control NOT gate. Okay, so the control NOT gate is defined by its action on the qubits. For example, I is the control qubit and J is the target qubit, and exclusive OR is exclusive or defined by this one. So as you can see, we have here the CNOT gate. This is how we program it on a quantum circuit, and this is how we represent it on a classical computer. So as you can see, the rule for classical NOT gate, I mean the control NOT gate is whenever the input qubit is 0, the target it will not do anything to the target qubit. But if the input is 1 and the target, if the input is 1, it will flip the target qubit. For example, here, if it's 0, it will of course remain 0. If it's 0, 1 will still remain 1. But if the input is 1, it will flip the target qubit, which makes it into 1. And if it's 1 again, of course, it will gonna flip it and make it a 0. Okay. So what we can do now, let's try to code this control NOT gate onto our this one, our coding platform. So to do that, of course, let's try to do a quantum register, and then let's have our quantum register input, which is 2, and then we have our name. Let's call it Q0, and then we have our classical bit register, classical register. Okay, and then let's name it as number. Let's have a 2 classical register, and name it as CO. And then let's initialize our quantum circuit. So to do that, let's have our variable QC, quantum circuit. We have to pass the registers, right? And then, okay. So what we can do now is to create a barrier, which is this one. Then to do this gate, what we can do is to work with CNOT. So QC.cx, and then it takes 2 parameters, okay? The control qubit and the target qubit. So let's use 0, which is this one, and the target qubit will be the second qubit. So let's pass it, and then let's measure the 2 qubits. So QC measure 0, 0, and QC measure 1, 1. Then let's try to draw it. Okay. Draw. Then output. Okay. MPL. Okay. So let's try to run. Okay. Now we've been able to make this work. Okay. And then the next step is to simulate the circuit if the input of the first qubit is 1 and the second qubit is 0. So remember that the input of the classical registers are always default to 0. So what we can just do is to flip the input of our first qubit. So to do that, let's have the gate, the NOT gate. Okay, so it's just going to flip the gate from 0 to 1. So let's click run. As you can see, we have it here, and then we simulate it. Okay, and then let's pass the simulate QC. Okay, and then let's click run. Okay, so as you can see, we have this outcome with possible 1 1. So why is this the outcome that we have? So remember, okay, so remember that when we work again with the drawing, so remember that if the in the control qubit is 1, it will gonna flip this this target qubit. So this is 1, right? And of course this one is 0. So the measurement will become 1, and then it will gonna flip the 0, which makes it 1 1. Okay, that's why we have it here as a 1 1. Okay. Okay, so what's wrong with our code? Okay, oh, Python. Yeah, that's one of the advantage or disadvantage of Python. We need to do the indentation. Okay, okay, for our last two exercise, okay, which is exercise 6 and exercise 7. So what we can do is implement the circuit below as code, and let's use the control NOT gate. So to do that, of course, let's just copy paste the code above to make things faster, okay, and just modify it, okay. So as you can see, we have a quantum register, and we need to have at least 3 quantum input register. So to do that, let's just change it to number 3 and name it as a QIN for a quantum input. And then we also need to have a quantum output register. So let's initialize one quantum register. And then we only need one, right? One. And then the name. Let's name it as Q out, Q out. And then for our classical register, we only need one. So let's just make it one, and let's name it at C out. Let's name it. Let's name it C out. Okay. And then after we've created the required number of qubits and the bits, we then apply a barrier. Okay. Let's apply a barrier. QC that barrier, and then let's create a control NOT gate. So let's use a control NOT gate on our control qubit index 0, and on our the fourth qubit, which is on index 3. So to do that, QC.cx 0, which is the first qubit, and the target qubit is index 3, which is our fourth qubit. And then let's do again the other control NOT gate, which is on our 1012 second index and our third index. So to do that, let's apply QC.cx and then to number 3. And again, let's create another barrier again. So QC.barrier, and then let's measure the quantum output register. Okay. So QC.measure 30. So let's delete the code that we don't need. Okay. Let's comment this first. Okay. Okay. So what's the problem? Oh, we didn't pass the other quantum register. So let's add it there. Okay. So as you can see, this quantum circuit is the same as the quantum circuit above. Okay. So now for our last exercise, okay, before I transition it again to Sir Bobby, let's try to implement this function to say that if the input is 1, 2, or 3, it will going to give us either true, 1, 0, or 1. It can be a true, false, or a true. So to do that, let's copy this one and then put it here. Then let's comment this one out and then uncomment this one. Then what we can do is to check if the first, if it's 001, it should give us a 1 value. So to do that, we're just gonna put an X gate under the first qubit. Okay. Then if we run it, as you can see, it gives us a 1 value. Okay. So this one equates to a 001, right? Okay. Then the next thing we need to do, let's try to use 010. So to do 010, what we can do is to apply X gate on our second qubit. So let's just pass the index. So this one is 010. So if I run this one, it should give us an answer of 0. Oh, yes, we have here the 0. It's our outcome. And then the last one is let's create a tree representation, which is equivalent to 011. So to do that, let's just uncomment our first qubit and our second qubit to create 011. Okay. 011. So it should give us number 1. Great. Okay. So now that's gives you the idea how to like program with quantum computers. And if you still would love to enjoy working with the further problems, we have exercise 8 to exercise 12 for you. So thank you very much. Back again to you guys. Thank you.
So thank you very much, Asher, for that wonderful demonstration of how to program in Qiskit. So since this presentation is also streamed in YouTube, you can I'm sure that uh, that it's quite hard to to understand it at first hearing, but you can just replay the presentation in order for you to understand quantum computing, to be able to understand how circuits are created. Just view again this presentation, and if we would like to invite you to join our group. We actually have a Facebook group in Facebook and a Slack group. So we will just give the details to Daniela, and so that's it. I'll turn this over to the MC. Thank you.
Wow! Talaga namang napaka-mind-blowing ng topic natin for today. Quantum computing is really broad pala, partner. It even covered machine learning, artificial intelligence, cybersecurity, and different algorithms that would solve problems in modern computing. That demo by Mr. Asher is also great because everyone in the seminar had a chance to try and experience quantum computing using Google platform. Ikaw, partner, ano namang masasabi mo sa naging lecture natin ngayon?
Oo nga, partner eh. Grabe. Hindi nakalang may ganyan pala sa field natin. Kasi akala ko sa mga Marvel movies lang yung quantum na yan eh. For me lang ha, I think this topic is very interesting and one of the uncharted lands when it comes to the field of technology. Well, at least para sa ating mga beginners or aspiring programmers. Personally, maganda na nagkaroon tayo ng opportunity para malaman to since ano to eh, I feel like malaki ang potential application nito sa future innovations in technology.
Saka, isa pa, di ba? Ang swerte natin kasi isa sa mga experts ng quantum computing talaga yung nagbigay sa atin ng talk for today. Kayo naman guys na nasa audience, are there any questions in the topic? I'm sure our speaker for today will be more than happy to answer inquiries. With that being said, let us open the question and answer portion for today's talk. To those guys who are watching in YouTube po, you can type po the questions in the chat box below and I will read it for you. And now the floor is open for your questions. You can type it guys ha sa ating mga chat box, or you can speak up. You're allowed to speak up in this point of our talk. Thank you.
Bago sila, habang nag-iisip pa sila, habang nag-formulate pa sila ng question nila, nung nakikinig ako, sa una pa lang, may naisip na akong question. Although medyo childish, please forgive me. Pero Sir Bobby, tanong ko lang po, possible po ba na yung, di ba po merong quantum computing application sa machine learning or AI? Is it possible po ba na magkaroon po tayo katulad nung Jarvis katulad sa Iron Man?
That's really a very good question, no? So, some scientists believe that yung human mind, no, is a quantum computer. Although right now, no, if you think about it, the quantum computers being created are, for example, in IBM, it's using superconducting qubits now. So it seems that why is it that we don't carry a super cooled what you call this, a very cold storage in our brain, no, in order to do quantum computing, but probably we just don't understand the mind yet, no. But very reputable scientists, they believe that the mind is a quantum computer, no. So if the mind is a quantum computer, if we have that premise, then to be able to have an intelligence just like Jarvis, no, it should be possible. So even right now, no, we can have those assistants, no, but it's like Alexa and who's this and Siri, no, which are not perfect, no, but when we have sufficient qubits, like sufficiently many qubits, logical qubits, no, I think we would be in for a surprise, no. So imagine this, no. We have a neural network algorithm, no, and then there was this. So in your neural network, you have the input and output layer, no, and then you have hidden layers, no. And then they said, oh, we can three layers are enough, no? 3 layers are enough. I think what the reason for that is we don't have the computational capability in order to have more than 3 layers, no? However, it turns out that when this hardware, no, called graphics accelerators, CUDA, they came out, and then what we did is to offload the computation to those graphics accelerators. It turns out that we can add more layers. And then what happened is that the more layers translated to more precision, no? So before, you would be lucky to have 70% success rate in your face recognition, right? But right now, face recognition is very powerful, no? And like we have more than 95, no? We have 98% precision, no, of facial recognition, and that was unheard of before, no? Before the advent, no, of this CUDA, we never knew that we can do that. Now imagine when we have sufficient qubits, sufficient number of logical qubits, I think we would really be in for a surprise, no? So that's something to look forward to in the future. yeah, so yeah, it would be possible.
Thank you, Sir Bobby. Meron po tayong questions from one of our viewers from YouTube. It came from Mr. June Abraham Surendera. The question po is, what are the biggest differences between classical and quantum programming?
Oh, that's a really good question. Huh? Um, so, gonna the classical well, when you do quantum programming, no, you don't abandon classical. Okay, that's one thing. Okay, so you can think of a quantum computer as like your graphics accelerator, no? where you want to offload very complex computations into the quantum computer, just like you offload to a graphics accelerator. So which means you still need your Python, yeah, you still need your programming language that are running in classical computing realm, no? Now, in terms of paradigm, it's different, no? So now in classical computing, we know that 1 + 1 = 2, no? But in quantum computing, it's different, no? Because you are making the qubits in superposition and then applying gates. When you apply gates, what happens is that it actually influences the probability amplitudes. No? So some states, no? Some states, kasi ano to when you do superposition states, what happens is that your qubits become a combination. No? It's like at once, no? All of them have all the values of the numbers between 0 to 2 to the n, no? If you have n qubits, no? 2 to the n minus 1, they are there, no? And then, so how do you, so the challenge now is how do you create an algorithm in such a way that the answer to your question is the one that has the highest probability of being measured. So it's different, no? That's why it's for one thing, it's hard, no? Shor's algorithm is the algorithm that that allows you to decrypt theoretically the RSA, no, and elliptic curve, no. But if you take a look at how Shor's algorithm was programmed, it's very different, no, from the way we do classically, no. And then it's also a hybrid between computation in the quantum, and then once you measure it, it will give you a number, no? And that number, you will have to use a classical computer in order to further derive what is known as the period, no? So once you get the period, you can now decrypt your decrypt the cipher text, no? So ano siya, it's a different mindset, no? It's not straightforward, no? Even loading your data, no, in a quantum computer is different, no? In classical computer, you just read it, no, and then it becomes a sequence of bytes in your computer, no? But in the quantum computer, when you load your data, it becomes this amplitudes, no? You map it to the amplitudes of your qubit. So it's a different way, no? And yun nga, it's probabilistic, no? So when you measure your quantum computer, well, when you measure, so when you run your algorithm and then you measure it, you don't measure it only once. So you have to measure it multiple times in order for you to get a probability distribution, no? Or in order for you to be able to get the to be sure that the highest occurring number, to get the highest occurring answer, because that's the one that the quantum computer tells you that that's the answer. And so in terms of paradigm, no, that's one thing. And also here, no, it's your your mathematical background comes into the picture, no. It's because when you design circuits, no, and you want to so designing circuit itself is is a difficult task, no? And then proving that your circuit will give you the answer with high probability is a mathematical problem, no? It's also quite difficult, no? But so that's the reason why we need to influence our education system, no? We need to put these concepts as early as possible, no, to the educational to the child's education, so that they will just this will just become like an ordinary conversation for them, no, not like us where this currently like something big, no, it's a big deal. But ultimately, once quantum concepts creep into the educational system, and together with all of these ways to learn, no, like videos in YouTube, no, online learning, which we did not have before, no, especially in my time, no. When I was in high school, we didn't have a computer, no, we only have books, no, and now you can just ask someone from the internet about the answer, no? So imagine that happening right now, what more in the future? And so which means that our kids will ultimately they will be learning advanced concepts at a very early age, no? At a very early age. So yun yung ano, no? So sa quantum computing, mathematics is also important, no? And of course, just like I mentioned earlier, if you have a quantum computer but you don't know how to formulate your problem, it's also useless, no? So that's why formulating a problem which doesn't need a quantum computer, no? It only needs your brain, no? Is also very important, no? It becomes very important. So yeah, so it's a different kind of programming, no? So nakita niyo naman, no? It's based on circuits, no? One of these days, no, you don't need to program in circuits, no? You just need something like a factor number, no? And then if you factorize the number for you using a quantum computer. But at this stage where it's still very new, no, we should learn the foundations, no, first, no. Let's not go yet. Let's not go. It's very easy to go to the higher level, no, but to understand what's underneath is our job, no? As a programmer, we need to know what's happening. We need to know this language. This is not just a new language, no? This is a different kind of computing, no? Alam niyo naman, no, yung computing. When we say computing, we talk about Turing machines, no? We talk about finite state automata, no? That's the kind of computing that is it's a different, that's the kind of computing I'm talking about, and it's different in quantum computing. Yeah, so many things, no, many things. Like I mentioned earlier, tunneling, diba? Tunneling. Imagine being able to tunnel through the minima, no, of your of the function that you are trying to minimize, no? And also being so that's one, tunneling. And entanglement, no? Entanglement, being able to, for example, the quantum key distribution, no? Being able to determine that someone is eavesdropping, no? Because when someone eavesdrop, what will happen is that they will measure the quantum system in order to get the value, no? But when the quantum system is disturbed, it will then settle into a known value, and you can detect that, no? That someone has tampered. So yun, I hope I was able to answer your question.
Yes, sir. Thank you po. I can see that there are still unanswered questions in our Zoom chat box and in our YouTube, but sad to say na we have to cut up na po our question and answer portion. But don't worry po, those questions po na hindi nasagot ay pwede po nating ilagay sa ating feedback section sa ating evaluation form later. Then, to proceed po, dadako na po tayo sa awarding of plaque. May we thank Mr. Bobby Corpus and Mr. Asher Manangan for entertaining the questions of our audience. Now, we are awarding our speakers, the pioneers of One Quantum, this appreciation plaque as a token of gratitude for taking the time and sharing the knowledge to our audience.
This plaque of appreciation is given to Sir Bobby O. Corpus Jr. for sharing his valuable insights and expertise in the seminar entitled Quantum Computing, Are You Ready for the Future of Computing? Via Zoom, given the 7th day of November 2022 at the Technological University of the Philippines, Ayala Boulevard, Ermita, Manila.
Excuse me, sir. May we request po na open po yung cam po ni
Okay,
Mr.
thank you.
Asher and kami rin po ni partner event. Then next, we are also awarding this certificate of appreciation to Mr. Asher Manangan for demonstrating his skills in virtual webinar entitled Quantum Computing, Are You Ready for the Future of Computing? Conducted on November 7, 2002, given the 7th day of November 22 at the Technological University of the Philippines, Manila.
Thank you very much.
Thank you, guys.
Last but not the least is this certificate of participation awarded to our audiences for their active participation on this virtual webinar entitled Quantum Computing, Are You Ready for the Future of Computing? Held on November 7, 2022 via Zoom, given the 7th day of November 2022 at the Technological University of the Philippines, Manila. We would like to remind our participants to check the Google Forms link to be provided later to acquire your certificate for attending this webinar. Failure to fill up this form will prevent you from getting the said certificate. Sir Bobby, meron pa po ba kayong short, sweet message para sa mga audiences natin? I'm sure parang meron po kayong short advice po para po sa mga interested sa quantum computing or even sa mga computer studies students.
Yeah. Yeah. Yeah, so siyempre, I've been a programmer for a long time now, and I'm sure all of you will one day, in your after graduation, you become programmers, no? So yung ma-advise ko lang is first, do not waste time, no? So sabi nga nila is the number of hours that you spend on learning a subject, no, is will make you become an expert in that. No? And there's a number of hours, no, which is 10,000 hours will allow you to become a professional, no, or kung sa ano pa sa piano pa or sa violin virtuoso, no. So don't waste time, no. And so that's from the programming part, no. Another one is make sure that you always you don't forget the basics, no. Foundation, no? So for example, alam naman natin na whenever we program in high level, no. So whenever we sort something, we just apply sort, no. Whenever we search, we just apply search, no. But we still need to know how these algorithms are actually being implemented, no? Because by knowing how they are implemented, one of these days you will be asked to create, no, something, and then you will be able to to apply your experience, no, on creating algorithms that are efficient, no, to your programming, no. And I think also for quantum computing, especially now, do not be afraid of the mathematics now. It's now time for you, if you are really serious now in your career into IT, to really take things, really study, no? The fundamentals, especially the increase your mathematical knowledge, no? Or kasi like for me, no, I have always studied, no. Hindi ako nag-stop mag-aral, no, nag-graduate ako many years ago, no. Many years ago, but until now, no, I'm still doing mathematics, no. Even if I'm not in the academe, no, I'm still reviewing. I'm still you learn by doing, no. Read research papers, no. Kasi these are very important, no? If you really want to become a world-class programmer, you have to first you have to aim to be a world-class programmer. Yeah, you have to aim high, no. Ika nga nila, no? If why fly like a barnyard hen when you can soar like an eagle, no? So that should be your attitude, no? In life, no, and especially in this in your endeavor, no, as a IT professional. And then for quantum computing, no, you really need a pencil and paper, no. So get pencil and paper and then write the equations, no. Hindi pwede na titingnan mo lang siya, no, and then because if you cannot solve a problem, no, it means you don't really understand it, no. So that's why advice ko, if you want to learn quantum computing, no, pencil and paper is the best way, no. Of course, you can use like what you call this, the computer algebra system, no, to solve your equations, but at least being able to do that, no, that's you apply a computer algebra system for very large scale problems and for very small problems, no? Like for example, 2-qubit, 3-qubit system, no, you just use a pencil and paper, no, and in that way you will learn, no, especially yung Bernstein-Bazarani algorithm that I presented, no? There was one slide there which says that in fact this circuit is equivalent to this circuit, no. So why don't you get a pencil and paper and then prove that it's equivalent? And then from there you can understand, that's why Bernstein-Bazarani works because these two circuits are equivalent. Yeah, so that's it. No, so don't forget. I hope that you can subscribe to our YouTube channel. This actually for para talaga to sa bayan. No? Our purpose in One Quantum, we're not earning anything, and and also our purpose is really to make more Filipinos aware, no, of quantum computing. But it seems that it's really very hard for us, no? Kasi it's hindi naman nagvo-viral yung mga ganito eh. So it's just so hard, no? So, and kaya ang I'd like to ask you a favor, no? If you can subscribe to that, and then you probably by subscribing you will help in making this more the subject making more Filipinos aware. James is subscribed to this YouTube channel. Probably it's really interesting. No? Well, maybe I can subscribe as well. So that's one thing. And also, please join our Slack. No? If you're really interested, no? If you're really interested in learning, no? So join our Slack channel. There you will meet like-minded people. So that's it. Thank you very much.
Thank you, Sir Bobby, for giving us such wonderful insights. I would like to remind everyone about the link to be filled out in order to acquire your certificates. And in the next slide, here are some of the links you can follow if you are interested in learning more about quantum computing and, of course, One Quantum Philippines. As we wrap things up, the students of the SITNS 4A Internet Explorers Group would like to thank everyone, our participants, our speakers, Ma'am Francisco, and to Mr. Alfaro for guiding us to create this successful program. I think gusto pa pong mag-closing remarks ni Mr. Alfaro. So may we give the floor to him and let us give our undying attention to Mr. Alfaro. Thank you.
Hello, good afternoon. Narinig na ba?
Yes po, sir. Good afternoon po.
Sir,
I would like to thank the speaker, Sir Bobby Corpus, for his time and sharing his knowledge and expertise in quantum computing. Second, I hope the students learned a lot from him, and I'm sure of that. Second, I would like to commend the efforts of this group in conducting a successful activity. So, congratulations sa inyo, and konti na lang konti na lang requirements ang isasubmit ninyo at pwede na kayo mag-concentrate sa inyong mga thesis, respective thesis. And then third is I look forward to other groups to conduct similar successful seminar like this, or training or seminar workshop. So kindly remind the participants and the organizers how to get their certificates. So yung kay Sir Corpus, ihahatid na lang yung plaque of appreciation, definitely.
Yung plaque, sir, ipapadala. Medyo
Maraming
delayed lang po.
salamat po, sir.
Salamat.
Sana po hindi ho kayo magsawa na mag-talk sa amin kung ibang topic naman kung inyong mamarapatin. At again,
No problema.
congratulations to this group. Job well done. Thank you.
Thank you.
Thank you, Sir Alfaro. Special thanks to Sir Negado, Sir Lee, Sir Tumagan, and Ma'am Monino for taking the time to attend and invite their students. Not just as special guests, we are also very grateful to everyone who watched and participated in this event. Everyone in this room, may I ask you to open your cameras for our documentation.
before we end our activity, I would like to thank also the faculty members who allowed their students to attend this seminar. Maraming salamat po sa aking mga kapwa guro sa Computer Studies Department, and also I would like to thank the department head for allowing us to conduct this kind of activity. Maraming salamat po sa inyo lahat.
Everyone, thank you for cooperating, and we are now concluding the end of this webinar. Thank you guys. Thank you. Maraming salamat.
Thank you so much.
Thank you.
Thank you po. Thank you po. Thank you po,
Guys.
sir.